We are going to look at the polarity of molecules, and first we're going to start off with just a review of polarity of bonds. So if I just have two atoms, we can look at their bond polarity. So this, notice the arrow is pointing towards atom B, which, as we talked about in class, indicates the electrons are being pulled towards this side. Because the electrons, although they're being shared, are not spending as much time on atom A, we see the partially positive end labeled with A. And so if we look at the electronegativities, we can see why this is the way it is, and that's because atom B has a higher electronegativity than atom A. If I were to change so that they have equal electronegativities, notice that we no longer have any dipole moment. There's no longer any polarity. So that, again, is what we talked about. So again, this is for just a single bond between two atoms. If I move to a molecule that is made out of multiple atoms, then the situation is a little bit different. So I'm actually going to change this to be more representative of real atom with a real molecule with the higher electronegativities as the terminal atoms. So notice that, hold on, let me set this all up here. So notice that we can look at individual bond dipoles. So as you'd expect, if you look at the electronegativities we have up here, atom A and atom C have equal electronegativities, and they are greater than the atom B electronegativity. So we see that the electron density is being pulled towards atom C and towards atom A. And now if you notice the alignment of these atoms right now, it is linear. So that means that all the atoms are in a straight line. So even though I have bond dipoles on each between the B to C atom and the A to B atom, if I look at the overall molecular dipole, so this would appear as a yellow arrow, overall this molecule is not polar. And so like if I turn on this electric field, that's how we can actually test and confirm whether or not something is polar or non-polar overall. If you apply an electric field to it, the molecule doesn't do anything, so I'm turning it myself, but it is not responding to these fields. So that means that this molecule overall is non-polar, and the fact that we don't see this yellow molecular dipole arrow also confirms that. Okay, so what would happen if I didn't make this a linear molecule? So I'm going to shift this way. So notice that as I shift this way, now the reason this would happen, something not being linear, is if remember if we have a pair of non-bonding electrons here, I wouldn't be able to see them, but they take up space, and if they take up space, then these two arms are pushed closer together than they would be if there wasn't a pair of electrons out here taking up space. So notice that when I don't have that linear shape, but when I have the bent shape, I end up with the overall molecular dipole in this direction. So you'll notice that, if I have the partial charges labeled, we have a partially positive charge on atom B, and then the partially negative charges on atoms A and C. And so this molecule, again, if I try to rotate it in space, notice that the partially negative side is attracted to the positive plate, partially positive side is attracted to the negative plate, and so we can tell this molecule is in fact polar. And so the reason it's polar is because it's not symmetrical. And the thing that we have to be careful about is when we say it's not symmetrical, you might look at this and say, well, it's got the A and the C are both out on both sides and they're, equally spaced apart. That looks symmetrical to me, but again, we want it to be like symmetrical 360 degrees all the way around. So typically we're going to see molecules that have non-bonding or lone pairs of electrons causing an asymmetry, so causing the molecule to be not symmetrical, and as a result, those molecules tend to be polar. Just to look at some real molecules as an example. So again, here's hydrogen fluoride. So if this is a polar bond, which it is, then we're going to end up with a polar molecule. So that's not a surprise for a molecule containing just two atoms. If I look at another example, so let's look at borane. So that's BH3. And let's label the atom electronegativities. So notice that boron and hydrogen, their electronegativities, the difference is only 0.1, so we wouldn't expect these to be polar bonds anyway. But notice this is a symmetrical molecule, so I turn it around. This is the, see if you can guess the shape, but it's the trigonal planar shape. And so notice all of the terminal atoms are in the same plane with the central atom. And so this is a symmetrical shape. It's symmetrical all the way around, 360 degrees, and but it contains nonpolar bonds anyway, so it's a nonpolar molecule. Let's take a look at another one with the same shape, so boron trifluoride. So notice boron and fluorine. Now this is a covalent bond, despite the fact that we have this huge electronegativity difference. So again, this would be one of those molecules that can't be categorized like we discussed using electronegativity differences. But anyway, again, the shape is trigonal planar, so all the atoms, terminal atoms, are in the same plane with the central atom. So notice, though, that even though each of these individual bonds is polar, so electron density is being pulled towards F with each of these bonds between B and F, notice that we don't see the yellow arrow appearing anywhere. So what's happening is that, and again, this is kind of more a physics thing that we've looked at, vectors, which are directional arrows. If we add up all of the, the directions and the magnitudes of these arrows, because they're equally spaced out around the central atom in the same plane, their net effect is that they cancel each other out. And so, there's no, notice that like each of these F's would be the partially negative ends. There's no partially positive ends sticking out anywhere. Okay, and so if there's no oppositely charged ends, then we do not end up with a polar molecule. So this molecule, even though it contains polar bonds, is nonpolar. And notice that it is symmetrical. And again, there's no non-bonding pairs of electrons. So trigonal planar, if you looked up the information we have on that shape, there's 3 atoms attached to the central atom, 0 non-bonding pairs of electrons. So that's symmetrical and nonpolar, despite the fact that it contains polar bonds. Let's look at another example here. So CF4. This contains polar bonds. So carbon and fluorine, there's their electronegativities. The difference is 1.5. Those should be polar covalent bonds. We look at our individual bond dipoles, and those are being pulled towards the fluorines. So, all the F's would be technically like partially negative if you look at how the electrons are being distributed. But despite the fact that this contains polar bonds, now this isn't in a plane like the trigonal planar, so it's not quite as obvious and easy to see. But again, if we were to add up all these vectors, again, take physics if you want to know more about that, because these bonds are equally spaced all the way around the central atom, and there's no there's no imbalance in that pull-on electron density from carbon. This is symmetrical all the way around, and this molecule is nonpolar overall. So again, we don't see the yellow molecular dipole coming up. So tetrahedral and no non-bonding pairs of electrons on the central atom, and so that is a nonpolar shape due to its symmetry. Now let's watch what happens though. So we have to be careful with making blanket statements about, tetrahedral is always nonpolar, because if we were to change this a little bit so that it wasn't so symmetrical, so let's look at what happens if I were to replace one of the F's with an H. Okay, so CHF3 is what we're going to look at. So notice now that instead of having a polar bond between C and F up here, I've got a nonpolar bond, so H and carbon have a nonpolar bond on one side of the molecule. So notice that we now see this yellow molecular dipole arrow showing up. And so the electron density is being pulled towards this bottom side of the molecule where all the F's are. So, and the F's are all pulling electrons, unequally sharing them with carbon and pulling them towards their side of the molecule. Hydrogen's not doing that though. So this bond between carbon and hydrogen, they're pretty much equally sharing those electrons. And we end up with an overall net molecular dipole, meaning this is a polar molecule now, because by replacing one of the F's with an H, even though we still have that same tetrahedral arrangement, we have wrecked the the symmetry in that this bond over here is not as polar as these bonds over here. So it's not balancing out that electron pull on this side of the molecule, and so this molecule does end up being polar overall. If we look at some other examples of tetrahedral arrangement. So if I were to replace two F's with two H's, notice that we have this overall net effect that's even greater in this direction. So again, the hydrogens sharing their electrons with carbon pretty equally, and the F's are not, so the electron density is being pulled towards this side. This would be the partially negative end. This is the partially positive end. Let's look at some other shapes. How about, let's look at ammonia. So ammonia has the tetrahedral electron arrangement, and if you draw the Lewis structure for ammonia, you'll notice that nitrogen has a non-bonding pair of electrons on this side, and there's 3 hydrogen atoms attached. But again, what I said earlier, was that non-bonding pair, because there's not an atom up here to balance out on this side, this ends up having an overall partially negative charge on the nitrogen being more electronegative than hydrogen. You can see that down here. And so, although, again, you might say, well, this looks like a symmetrical molecule, again, this fourth region of electron density, and I'm pointing here like you can see something, but again, the lone pairs, we know they're there from when we draw the Lewis structure. We know they take up space from what we talked about with Vesper theory, but that non-bonding pair can't be seen when I look at the geometry, but it still is impacting the shape. So there's not anything over here to balance this, pull on electrons between nitrogen and hydrogen. If there was another hydrogen here, that'd be a different story to balance out this side of the molecule. So with the presence of the lone pairs, that causes the asymmetry in the molecule, and this ends up being a polar molecule. So in summary, our shapes that tend to be non-polar shapes, as long as all the bonds are equal. So as long as all the atoms attached to the central atom are identical, the symmetrical non-polar shapes tend to be linear, trigonal planar, and tetrahedral. Now again, we already looked at some exceptions to that, where if we have a different atom attached on one end than on the other in any of those shapes, that might then result in polarity. But if we have all the same terminal atoms and we have linear, trigonal planar, or tetrahedral, those are symmetrical shapes, and we will have non-polar molecules overall for those shapes. When we look at the shapes that have lone pairs attached, that causes asymmetry. So those shapes would be bent or angular, or pyramidal, trigonal pyramidal. Those two shapes tend to be polar shapes. And again, that's because of that presence of the lone pair of electrons on the central atom. Its presence takes up space, but when we look at the overall polarity of the molecule, there's nothing on that side. There's no other atom sharing electrons with the central atom on the side where the lone pair is to balance out the dipoles, and as a result, we end up with a polar molecule overall, as long as there are polar bonds. So again, our asymmetrical shapes, which then result in the molecule being polar overall, are the bent and trigonal pyramidal. So that is polarity. Again, you need to identify the shapes and look for the presence of lone pairs of electrons in order to make a determination of polarity.